After the previous chapter, in which we extracted the Atmega from the Arduino development board to reduce its size and power consumption, this chapter will focus primarily on the latter one, the power consumption. We will discuss the facilities that are integrated in the Atmega itself to increase the battery life. First, in this chapter, we reduced the power consumption by scaling the clock frequency. In general, the slower the clock, the lesser the power the chip consumes. However, the downside is that the computation is slower as well. Is there a sweet spot in which we can reduce the frequency without impacting the computation facilities? Answering that question is followed by deactivating the unused peripherals using the power reduction register. Then we can also command the Atmega to sleep. For instance, in many projects, the chip has to wake up every now and then to measure the temperature or to check the light intensity. Currently, in between, the Atmega runs in an endless while loop waiting for the time to pass. In fact, most of the times, the Atmega is busy just running in that loop without contributing. Hence, it would be much better for the battery life if the Atmega can be powered down during the breaks and some alarm exists to wake it up again, do its task and go back to sleep. In this chapter, we will learn exactly that. And briefly, we will talk about the unused pins and two more interesting and new peripherals, the Watchdog Timer and the Brown-Out Detector. Let's get started. This table shows various settings and how much current the Atmega typically draws. For instance, if it is active, that is, it computes something or waits in a while loop, it will consume 5.2 milliamperes in average, when it is clocked at 8 MHz. If the clock is halved and VCC is reduced to 3 volts, the current cuts down to 1.7 milliamperes, a reduction by almost 70%. Depending on the mode the Atmega is set in, the current is different. For instance, there are two sleep modes, power safe and power down, which decrease the current substantially. We will talk about the sleep modes in a bit. For now, we will concentrate on VCC and the clock frequency in active state, set into relationship in this diagram. On the x-axis is the frequency, and on the y-axis the typical draw of current, which in addition to the frequency also depends on a supplied voltage. First, we see that not all frequencies are supported for all voltages. For instance, if the voltage supply is only 3.6 volt, the maximum frequency is just over 14 MHz. As you can see, the higher the power supply in form of VCC, the higher is the current. And in addition, the higher the frequency, the higher the current. The diagram on the left is just a magnification of this part here. I calculated the power consumption for various settings based on the diagrams and tabulated them. First, we have to establish what power is. Power is the current multiplied with the voltage. So if either of them reduces, so will the power. In general, we do not have much control over the current. It is determined by the physical characteristics and structures inside the Atmega chip. But we can control the voltage and the clock frequency, as we already did in the previous chapter, in which we switched from the 16 MHz external oscillator to the 8 MHz internal one, essentially halving the clock frequency and hence the computation capabilities. From the datasheet, if the atmega is in an active state, that is, it computes something, waits in the delay_ms loop, or for a bit to go up since the corresponding peripheral becomes ready, or just sits in an endless while loop, it requires 9.5 milliamps typically when the clock is at 16 MHz and the atmega is supplied with 5 volt, as it is the case for Arduino. The total power is almost 50 milliwatts, that is for the chip only. I take this as the ground truth to calculate the processing capabilities, that is how fast the chip can process data and how much power is saved for the other settings in active mode. If we switch from the external oscillator to the internal one, we halve the clock frequency and therefore also the computation capabilities. In the end, we almost halve also the power consumption, which reduces to 26 milliwatt. If we reduce the supply voltage to 3.3 volt but keep the clock at 8 MHz, the computation capabilities will remain at 50% compared to the 16 MHz version. But the power consumption reduces to 21% of what we measured in the Arduino version. Now, if the CK-diff8 fuse is active, dividing the 8 MHz of the internal oscillator by 8 so that we get a clock frequency of 1 MHz, I have only 6.25% of the original computation power left. However, the power reduction is now at 96%. Just for the fun, let's clock the atmega with the slowest clock with deactivated clock diff8 fuse. The computation is below 1% of what it was now, but the power consumption is also at 1% of the original value. As you can see, selecting the right power supply and the correct clock frequency will result in a drastic power reduction and hence much longer battery life. Ideally, I would like to set the power supply to 0 volt and the clock frequency to 8 MHz to achieve maximum power savings without compromising the computation capabilities. But as you know, if the atmega is not powered at all, that is a power supply of 0 volt, nothing is going to happen either. So there are limits shown in this diagram. At 5 volt, but more precisely at 4.5 volt, the maximum clock frequency is 20 MHz. However, as the voltage decreases, so does the maximum clock frequency. It decreases almost linearly in a straight line. The Arduino runs the atmega at 16 MHz and 5 volt. So that is within the blue area and within the specifications. Sometimes you can run the atmega at 16 MHz and a power supply of 3.3 volt. However, it is not guaranteed to work since it is outside of the specifications. In the previous chapter, we used the low fuse to change from the external to the internal oscillator before extracting the atmega from the Arduino board. In this context, also the fuse CK-diff8 was introduced, which further divides the system clock by a prescaler of 8, the default setting for atmegas fresh from the assembly line. This ensures that the atmega can be used in all kinds of voltage settings. Modifying this clock diff8 fuse essentially changes the value the clock Prescale register is reset to. If unprogrammed, the register resets to clock PS equal to 0, If programmed, it resets to 0011. That means that this register and therefore also the system clock is configured even before the user program starts executing. However, the developer has access to the clock PR and hence can change the values while the program executes. To change the system clock, first the most significant bit called clock PCE is to be set, while all other bits are cleared. This enables write access to this register. Within 4 clock cycles, the new prescaler needs to be configured. To ensure that this operation is not interrupted, remember to turn off global interrupts or execute this code segment within an ISR, which ensures that the global interrupts are disabled automatically if nested interrupts are not used. So what are the prescaler options? Usually, the register value is either 0 or 3, which results in a prescaler value of 1 or 8 respectively. But other options are available down to a prescaler of 256, which has the potential to reduce the power consumption depending on the task at hand. There's one thing the developer has to keep in mind when changing the clock rate. We are used to give the clock frequency as a parameter during the compilation, like in this one. It is required for the delay_ms or delay_us functions. Hence, if the clock rate changes, those delay function calls will not be accurate any longer. But there's more to it. The block diagram on the right reveals that after selecting the clock, which is in this multiplexer, the system clock prescaler is applied at this point. This new clock is then fed into the AVR clock control unit, which uses this clock as a foundation to derive all clocks for the ADC, CPU core, RAM, and so on. And important to note, also for the general I/O modules. These modules include the communication periphery. Therefore, the selection of a different prescaler will affect the transmission speeds. To keep them constant, the configuration register for the communication hardware needs to be updated accordingly, such as the TWI bit rate register or the UART baud rate register. Especially for the latter register, the inclusion of set baud.h does not work any longer, since it depends on the frequency_CPU value. Once the clock prescaler bits have been set to the new value, the new clock becomes effective immediately. Since it is required to adapt the communication and ADC hardware to the new clock, it is advisable to change the clock prescaler only after the communication completed and not in between. The question now is how to select a clock frequency and how to determine which one is suitable. That we will discuss in the session handling how to make the atmega sleep, since both of them are related. For now, let's have a look how to deactivate periphery that a project does not require. Deactivating unused periphery is straightforward. A dedicated power reduction register allows a direct and easy access to this facility. The explanations of its configuration bits is self-explanatory. For instance, PR TWI deactivates the I2C or TWI hardware support if this bit is set. Overall, the timers, SPI, UART, and the ADC can be deactivated. If the deactivated hardware owns configuration registers, it is advisable to reinitialize those registers if the hardware is reactivated. One note though, if the developer uses the Arduino version of the delay function and deactivates timer 0 using this PRR, then this function becomes dysfunctional as it depends on this timer. If the developer uses _delay_ms, for instance, which is supplied by the AVR library, then there is no problem, as this function creates a loop whose number of iterations is based on the frequency. How much power does an active periphery cost in terms of power consumption? It depends on the state. If the CPU is active, the add-on ranges from 0.9% for the simple timer 0 to the ADC with 4.1%. Keep in mind that those numbers are in addition to the typical power consumption. Therefore, the power required by the peripheries in idle state is comparably higher, as these peripheries are not idling. But let's use some actual numbers instead of percentages. The typical current for an 8 MHz atmega running at 5 volt is 5.2 milliamperes. That is, if all peripheral hardware is deactivated. If the software developer requires the ADC, running it will cost almost 300 microamperes. Hence, these costs are added to the typical current draw, which results in 5.5 milliamperes now. An oblivious implementation, leaving everything turned on, will result in a final current draw of 6.4 milliamperes, an increase of almost 25%. The absolute numbers give the impression that with the reduction of VCC and the clock, also the power consumption of the periphery reduces. However, that is a misinterpretation, since with a lower clock and lower VCC, even the CPU draws less current. The difference of 25% remains the same. Therefore, deactivating the periphery when it's not needed and reactivating it when it is required reduces the power consumption substantially. The same is valid for the CPU and other peripheral components. If they are not needed, they should be deactivated. And that brings us to the sleep modes. We already saw that diagram, but let's have another look at the AVR clock control unit. There are multiple clock signals coming out, such as the clock for the input and output, the CPU, the ADC, etc. Depending on the requirements, this unit can control the clock signals individually. And if one of the clock receivers is not clocked, this receiver is turned off essentially. There are different sleep modes which deactivate the clocks accordingly. We already met one of the modes in the exercises about the ADC, which was set to the ADC low noise mode. As it can be seen in this mode, only the clock of the ADC and the asynchronous clock connected to timer 2 remain active. All other clocks, for instance the CPU and the I/O and memory, are turned off to reduce the noise. There is also the idle sleep mode, which essentially just turns off the CPU. Since the CPU does not execute the program any longer, also the flash is turned off. But there are more extensive sleep modes available as well, such as the power safe and power down mode, which turns off the entire clock tree for all components. We can conclude that in the power down mode, the power savings will be maximized followed by the power save, ADC noise reduction, and idle mode, which results in the least power savings. The last two sleep modes, standby and extended standby, we will handle in a minute to see the difference. First, let me show you how to enable the sleep modes. We have to set the desired sleep mode in the sleep mode control register. The sleep enable bit is basically arming the sleep mode. If SE is not set, the following call to sleep CPU, which puts the Atmega to sleep, will not have any effect. It is to protect any accidental activation by a runaway pointer or bug in the program. After all is set, sleep_CPU puts the Atmega to sleep with immediate effect. So what are the available values for the SM bits determining the sleep mode? If all SM bits are cleared in the sleep mode control register, the sleep CPU function call will activate the idle mode. Power down is 010, etc. If you do not remember all the bit values, the AVR library will help, as we will see in a bit. Okay, so how much power can be saved by activating the sleep mode instead of letting the CPU run in an endless while loop? The answer is quite a lot. With all peripherals deactivated, that is all bits in the PRR are set to 1, the Atmega in the Arduino setting, that is 5 volt at 16 MHz, consumes almost 10 milliamperes. Roundabout, that means that a battery which supplies 5 volt and with a capacity of 500 milliamperes will be empty in 50 hours or a little bit over 2 days. Just by activating the idle sleep mode in the same setting reduces the power consumption by 75%, meaning that the same battery lasts for 208 hours or 8.5 days now. Deeper sleep modes save more power. In power save and power down mode, the current that is drawn by the Atmega is 700 and 250 nanoampere respectively. That means that very same battery lasts for 3.5 and 228 years respectively. Obviously, those numbers are unrealistic since a CPU that is consistently in power down mode does not compute anything, and hence its existence in an embedded system is questionable. We already saw that the power consumption reduces with VCC and the clock frequency. Here in the lower part of the table, it becomes obvious that this is also true for the idle mode. However, if it comes to the power save and power down mode, the clock frequency becomes irrelevant and only VCC counts. It is obvious since in those modes the clocks are deactivated anyway. One curious thing that sticks out though, the maximum power savings are achieved if WDT is turned off. WDT stands for Watchdog Timer, and we will discuss in this chapter what that is and why it consumes comparatively a lot of power when in power down sleep mode. Okay, once the Atmega is sleeping, how does it wake up again? Depending on the sleep mode, several wake up functions exist. For instance, in idle mode, in which only the CPU and its flash memory are deactivated, the Atmega can be woken up from an external interrupt on the int0 and int1 pin, an address match on the TWI or I2C bus, through an interrupt in timer 2, the successful EEPROM or flash memory operation, the ADC conversion is ready signal, the Watchdog Timer, and any other signal through the pins. The number of wake-up sources reduces, the deeper the atmega sleeps. In power down, only the int0 or int1 level change, TWI address match, and the Watchdog Timer is able to wake up the atmega. Also, in this table, the differences of the standby and extended standby methods are shown. The standby mode is very similar to the power down mode, while the extended standby is similar to the power save mode. The differences between the modes is that the main clock source remains enabled in any of the standby modes. That means that if the external oscillator is used, the circuitry managing that oscillator remains active. The result is that the atmega can wake up incredibly fast from either of these modes. Usually, if the oscillators are powered up, it takes some time for them to settle. This time can be configured by the SUT fuse bits that we had in the previous chapter, and it can range from 256 to 16,000 clock cycles. However, if the managing circuit of the atmega remains powered during the sleep mode, the atmega is able to wake up within only 6 clock cycles. That comes at the cost of a slightly increased power consumption. Those timings, and hence both standby modes, only apply if the atmega uses an external oscillator. If the atmega is clocked by the internal 8 MHz oscillator, the startup time is always 6 clock cycles, independent of the SUT fuse settings. And that brings us to an interesting question. With the power of controlling the clock frequency and various sleep modes at our disposal, the problem that is to be solved is: given a fixed number of computations, shall those computations be done quickly so that the atmega can sleep longer, as shown on the left side, or shall the clock frequency and hence the power consumption during this active period be reduced, which results in the longer wake time and therefore shorter sleep? That question is a bit tricky to answer, and it definitely depends on the project. Imagine a situation in which the temperature is measured every second. After that, the average from the last hour, that consists of 3,600 measurements, is calculated. Shall it be done fast at the high clock frequency and high power consumption, or slowly at the lower power consumption? The graphs shown here represent the actual current drawn from a system with a maximum clock of 8 MHz and VCC of 3.3 volt without any activated periphery. The amount of computation is symbolized by the blue area, which is the same for both cases, 8 rectangular fields. At half the clock, the same workload takes double the time. However, the current reduces from 3100 to 1800 microampere. As you can see, we have not only the notion of voltage, current, and therefore power, but also power over time. And that brings us to the term work or energy. Energy is power P multiplied with time T, and its unit is watt-seconds, or also joule. We know the unit joule already. If we go to the grocery store and buy some snacks, its energy content is mentioned on the packaging. There are different forms of energy units. Instead of joule, calories might be mentioned on the label, or both, like in this case. There is some confusion regarding the unit of calories. A calorie written in lowercase is the amount of energy required to increase the temperature of 1 gram of water by 1 degree Celsius. To compute the energy in joules instead, the lowercase calorie needs to be multiplied with a constant of 4.184. The other calorie, this time starting with a capital C, is 1000 times the lowercase calorie and also called kilocalorie. Instead of increasing 1 gram of water by 1 degree Celsius, 1 kilocalorie increases the temperature of 1 kilogram of water by the same amount. Another form of energy is known from electrical appliances. To compare the projected costs of a new appliance, the amount of energy consumed over the course of a year is given in kilowatts per hour. Which means if you have an oven that constantly consumes 2 kilowatt for 1 hour, your electricity bill will reflect 2 kilowatt hours and your oven will be really hot. But back to our problem at hand. Let's compute the required energy to make an informed decision what we should do: fast clock rates and long sleep, or slow clock and shorter sleep. Checking the datasheet reveals that at 3.3 volt, the power down mode draws 4.3 microampere and in active state 3100 microampere. Now we check the time. In this diagram, the atmega is in the power down state for 4 seconds while it computes for 2 seconds. Summing that up, the energy consumed in both states gives us 0.02 watt seconds or 20.5 millijoule. How does it look like for the case with the slow clock? The power consumption for the power down state remains the same, since it is independent of the clock. The current drawn in active state reduces to 1.8 milliamperes. The time changes as well. Instead of 4 seconds of sleep, the atmega gets only 2 seconds and then has to work for double amount of time at half the speed compared to the previous scenario. Plugging in the values into the formula reveals that over the duration of 6 seconds, 23.8 millijoules of energy are consumed, which is 16% more than in the case with a fast clock. The reason is that the clock is halved, however the current does not follow the same rule. Earlier, the atmega required 3.1 milliamperes and now it is at 1.8 milliamperes, which is a reduction to around 58% and not exactly half. Therefore, in this case, it would be better to let the clock run fast and short while the sleep period is longer. In general, it can be said that it has more advantages to compute fast and to power save longer. That is also valid for a laptop. If it runs off the battery, it will last longer if the CPU is not limited in its maximum clock frequency setting. However, that statement is very general and does not have to be necessarily true. It depends on the situation and what the atmega is required to do. For instance, it looks differently if other sleep states are required, maybe due to the availability of wake-up sources, or if communications are involved which are usually magnitude slower than computations. For instance, if 1 byte needs to be transferred through UART using a constant transfer rate, that required time to accomplish the transfer is fixed no matter what the CPU clock is. Let's have a look at an example. Again, the energy required for the ATmega running at a faster clock is compared to one with a slower clock. However, this time, the communication dominates the wake time. In this scenario, the project required the communication via UART, adding 1.4% to the overall consumption while the ATmega is awake. No matter the amount of computation, the communication always needs 4 seconds to transmit all data. In this case, it is obvious which implementation conserves more energy. That is the one with the slower clock. However, in many cases, the implementation is a mix of computation and communication. Here, the communication of 3 seconds is preceded by a computation whose time requirement is influenced by the clock rate. The developer was quite smart. During the computation, the clock frequency is maximized. Once the results have been obtained, the CPU does not have to compute anymore, but just to communicate. Therefore, the developer dynamically scaled the frequency down to 1 MHz. It could also be lower, since as we know the maximum prescaler is 256 for the system clock. At an oscillator frequency of 8 MHz, the clock could have been reduced to approximately 31 kHz. Maybe the transmission speed required 1 MHz due to the error introduced when selecting unfortunate frequencies for the system clock and baud rate. Please refer to the UBRR calculations in the UART chapter for more details. Although the communication dominates the wake period, a bit of energy can be saved by maximizing the clock during computation. Let us add this discovery to the general rule. Ideally, the software implementation allows the developer to compute and communicate at the same time as shown in this diagram. If that is a possibility, it is advisable to stretch the computation by lowering the clock such that its time requirement ideally matches the time of transfer. Often, that sweet spot is not hit, but it is possible to get close to it. Doing so minimizes the time the CPU is awake without wasting CPU resources while communicating. After the computation or communication, depending on what needs longer, is complete, the ATmega can sleep again. In implementations, often the value that is to be communicated is also being computed. Imagine a project that measures the temperature and humidity every second. Both values are delivered by a DHT11. Usually, inexperienced developers would use the library for DHT, read out the sensor, and communicate the value in sequence. However, since the ATmega does not have a hardware unit able to understand the DHT protocol, it is bit-banked. So you can expect quite a lot of delay function calls in both reads, and a lot of precious CPU time is wasted in those delays and later on during the communication. Please note, before sleeping, the software developer makes sure that all bits have been transmitted by checking TX C0 instead of UDR E0. The first one indicates the complete transfer, while the latter one is set if the buffer is free to receive the next value that is to be transmitted. Parallelizing this problem is quite simple. While the new data is requested from the sensor, transmit the data from the previous wake time in parallel as shown in this example. First, the data is stored in the data register of the communication unit UDR0. We do not wait for the transfer to complete, but immediately start reading the next dataset from the sensor. Using ISRs, to send multiple bytes allows the read functions to continue almost uninterrupted, especially if the ISR is small like this one. This code can be further optimized, but it depends on how long the read functions take, which is determined by the implemented functionality and the clock. For instance, the communication can be a lot faster than reading the sensor. Hence the while loop in line 10 might not be required, since by the time the function reading the humidity returns, the transmission is complete. On the other hand, if the communication is very slow, the content in line 13 could be moved up to the ISR, since by the time the second byte is to be communicated, the reading of the sensor is already complete. How to implement this problem and how to interleave the communication with the computation requires a bit of timing analysis. Fortunately, the Atmega is equipped with timers that increment with every clock cycle. Therefore, the timer can be set up counting clock cycles that passed while executing the functionality of interest. Or in other words, the timer is used as a performance counter to profile a specific piece of source code. To ensure that the timer is able to count beyond its maximum value, an ISR can be used. That introduces a bit of noise to the measurement, but often this noise can be neglected or with a bit of effort even removed by analyzing the timer requirement for this ISR. Also note the order of resetting the timer. First, the overflow and then the timer value, hoping that no overflow occurred in the meantime. Since we just started the timer in this example, this is guaranteed. Once the number of required clock cycles has been computed, often it is required to convert this result into time. To do so, just divide the clock cycles by the CPU frequency that was set during the code execution. However, parallelizing components of the software only works if the system specifications allow it. It might be important to read the temperature and humidity and send those values immediately. In this case, it is advisable to minimize the time requirements for both. First, the computation portion by increasing the clock rate to its maximum if the compute code does not consist mainly of delay function calls, and second, the communication portion in which the system clock is minimized and the communication speed maximized. What else can be optimized in software? In this session, we will see how the sleep mode can be conveniently invoked by calling AVR library functions. Also, some tricks and tips for implementations are shown. Let's say there is an ISR that contains a shared variable called shared flag. It just sets the least significant bit to 1 in a simple operation once the interrupt occurs. And here is the main program. In the endless while loop, the shared flag is checked, and if it is set, it is cleared and some function is executed. If the shared flag is 0 and hence the ISR has not been executed, the if branch is skipped, global interrupts activated, and the Atmega is put to sleep. The SEI function call in line 15 ensures that the global interrupts are reactivated after the CLI call in line 9. This CLI and the SEI in line 12 make sure that while the shared flag is checked and eventually written to, those two operations, that is the check and the write, cannot be interrupted. Hence, the instructions are atomic and we will not miss any interrupts. However, This program might not exhibit the expected behavior. The intention was that all interrupts are handled before going to sleep. If an interrupt occurs after the SEI in line 12 and the sleep mode call, the shared flag will be set to 1 when the ATmega goes to sleep. Hence, this interrupt will only be handled when the ATmega wakes up again. To prevent that, it is desirable to minimize the time between the check of the shared flag and the sleep instruction as shown in this example. Instead of checking if the flag is set, it is checked if it is clear. Only then the ATmega sleeps. As long as the flag is set, handle_event will be executed. The chances that sleep mode is executed with a set flag are minimized by now. One might object and ask what happens if an interrupt occurs between SEI and sleep in line 14 and 15 right here. However, the SEI instruction is special as it makes sure that the following instruction after the SEI will be executed before any pending interrupts. You do not believe me? Have a look at the attached instruction set documentation for the AVR architecture. In this case, the next instruction is the sleep instruction. Therefore, this block is executed atomically. If the if branch is not executed and hence a bit in the shared flag was set, the bit is cleared atomically and handle_event is invoked. This enables the handling of the interrupt inside of the main while loop. This handling can then be interrupted again without utilizing nested interrupts. Okay, in this program, what else can be optimized? This atomic read, modify, write instruction of the shared flag is pretty messy. What if there are multiple ISRs? For every access to the shared flag, we have to remember to wrap it around CLI and SEI calls to prevent any interruption in between. In addition, both functions are so-called memory barriers, making it even worse. Memory barriers can be imagined as a gate in a program. Only if all values are committed to the memory, the CPU can continue to execute the program. This results in relatively slow accesses to the SRAM if the value is in the registers. Let's have a look how many instructions these 3 lines involve. I compiled the program. It is attached or can be found in the folder Course, Power and Shared Flag in the VirtualBox image. The relevant portion looks like this. First we see CLI. Then register 24 is loaded with the value of the shared flag, which is ANDed by -2 and written back in line 73. Since SEI is a memory barrier, which means that the new value for shared flag currently residing only in register 24 needs to be written to the location where shared flag is expected to be. As you can see, without the wrapping into CLI and SEI, this modification of the shared flag could go wrong. The 3 instructions required for the read-modified write operation to the shared flag gives ample opportunity to create a bug that is hard to find if the interrupt happens right in between. That makes the implementation prone to errors if the wrapper is omitted and forgotten somewhere, which can happen easily. Therefore, it would be nice if the update of the shared flag itself is atomic. While there is no option in this particular case, it can be achieved by modifying the program a bit. Fortunately, the Atmega has registers for general purpose. If the value of the shared flag is moved to that register, the value does not reside in SRAM any longer and hence does not need to be loaded, manipulated and written back. Therefore, the actual modification cannot be interrupted any longer. Here is the program. I just replaced the shared underscore flag with GPIOR0 and removed the CLI SCI wrapper around the read modify write operation. There are 3 general purpose I/O registers available in the Atmega and all 3 are at your disposal. They are not used by the compiler and do not have any effects to, for instance, the pin output. Hence you can use them for whatever you want. If the new program is compiled, the actual modify instruction becomes a one-liner in assembly containing a CBI instruction, meaning clear bit immediate with the address and which bit to be cleared as parameters. Again, it is attached or in a VirtualBox image under the mentioned folder. This instruction requires 2 clock cycles. However, since instructions themselves are not interrupted, the CBI call is atomic. Earlier, I mentioned that a developer does not need to remember all the bit values for the different sleep modes. Fortunately, the AVR library provides convenient functions to automate the sleep. First, there is the set_sleep_mode, which takes the desired sleep mode as parameter. While the functions are in sleep.h, the sleep modes are architecture specific and therefore defined in IOM 328p.h, which is included by io.h. Not all AVR architectures have all sleep modes. After setting the sleep mode, the function called sleep_mode enters the pre-configured sleep mode. The same function also sets the sleep enable bit and clears it again after waking up. This sequence can also be executed manually by queuing up sleep enable, sleep CPU and sleep disable. The last helper function is sleep baud disable, which deactivates the so-called Brown-Out Detector. What that is, we will have towards the end of this chapter. First, what else can we do to reduce the power consumption? Earlier, we had the digital input disable register 0 for the ADC and 1 for the AC, the analog comparator. If those analog devices are not used, and it is very unlikely that they are during the sleep period, except if the ADC samples analog values in the ADC low noise mode, both registers should be set to deactivate the digital inputs and to prevent a potential substantial power leakage. Let's have another look at the block diagram of a single pin. We have the part defining the data direction, the write pin and the read pin section. As shown in the diagram, there is one more section, and that takes as an input a signal called sleep. This line is set if the power down, power safe and the standby sleep modes become active. Its purpose is to disconnect the pin from the reading input section by turning off this switch here. The sleep is not active for pins which have a wake up function configured, such as the TWI address match wake up while sleeping. Also, the sleep signal is not set for any other sleep mode, but what shall we do with the pins which are not connected and hence floating? What if some fluctuation happens on those pins, which causes the read pin synchronizers to rapidly changing their state, burning a high amount of power? To prevent this situation, it is advisable to use the internal puller to put all unconnected pins into a defined state. Then nothing will start switching. To do so, just write a 1 to those pins in the respective ports while keeping the DIDR and POD bit at 0. That activates this transistor and charges this line. No power is consumed as this pin is not connected anyway, and once the synchronizers read the 1 from the wire, the value remains constant. Okay, let's talk about neglected peripheries. First, let's talk about the Watchdog Timer, which is a wake-up source for all sleep modes. However, it can also be deactivated to further reduce the power consumption, as we saw earlier. What does the Watchdog Timer do? The Watchdog Timer is quite interesting. The first curiosity is that it is always connected to the 128 kHz oscillator that we also saw in the last chapter and which we could select as a system clock. That means that no matter if there is a system clock or not, the Watchdog Timer is always independent of that clock. Then there's a Prescaler, and we can select one of those clock signals. WDE, WDIF and WDIE are configuration bits which we talk about in a minute or so. The output of the Watchdog Timer is an interrupt or a system reset. System reset? Yes, the Watchdog Timer has the capability to reset the entire Atmega, and then it starts its programming from the top. So what is the purpose of the Watchdog Timer? It is quite difficult to develop a program that reacts to all kinds of situations in the intended way. Many times, those embedded systems are deployed in hard-to-reach places, such as space, where it is costly just to go there and to press a reset button. It might happen that a situation occurs where the program goes into an unknown state. Imagine humidity creating a short circuit or radiation that the developer did not encounter before and hence did not even test it. To cover all situations, testing becomes extremely cumbersome and costly. Therefore, the Watchdog Timer was invented. It is a countdown which needs to be reset in intervals. For instance, here, the maximum value is 4 and it starts counting down from there. Then somewhere in the program is an instruction that kicks the watchdog and resets it to its maximum value. In case the program gets stuck somewhere and the watchdog is not kicked regularly any longer, it counts down and then issues a system-wide reset to bring the system to a known state. And since the watchdog has its own clock, it is quite independent and has all the tools to do so. To configure the Watchdog Timer to, for instance, how long that interval can be before it needs to be kicked again, the Atmega has a configuration register like for all peripheries. The watchdog interrupt flag is set if the watchdog times out and the watchdog interrupt enable, that is the next bit, is set. It is cleared by executing the respective ISR or by writing a 1 to the watchdog interrupt flag. If the Watchdog Timer is supposed to be used as an interrupt, make sure that global interrupts are enabled before making the Atmega sleep. The Watchdog change enable bit allows modifications of this control register within the next 4 clock cycles. To protect the Watchdog timer from accidentally overwriting it with new values by a bug in the program. It is important since the Watchdog timer could have the potential to fail the project if the program gets stuck and cannot be reset. To change any value in this register, set WDCE and WDE to 1 before overwriting it with the new values. The WDE together with the WDIE bit determines what the Watchdog timer should do once its countdown reaches 0. If both bits are 0, the Watchdog timer is deactivated. Only WDIE is set means that it issues an interrupt, while a system reset is going to be performed if only WDE is set. If both bits are set, then first the corresponding ISR is executed, followed by a system reset once the ISR completed. Maybe the program requires to sort something out before it is reset. That setting provides this opportunity. And there's another bit that is important for the Watchdog timer operation, and that is WDT-ON. It is not in this register since it is a fuse. If that fuse is programmed, meaning that it is 0, no matter what the bits of WDE and WDIE are, always a system reset is performed. Since fuses cannot be written to from within the program, it is a quite safe way to make sure that the Watchdog timer system reset always works. More about that in a minute. First, the Prescaler. Depending on the setting of the WDP bits, the time till an interrupt or reset occurs varies. The shortest duration is 16 milliseconds, while the longest is 16 milliseconds multiplied with 2 to the power of 9, defined as the maximum value. That translates to roughly 8 seconds. This example shows how to compute the WDP value for an arbitrary amount of time, here 1 second. If logarithms aren't your thing so much, you could refer to this table from the datasheet. Any other combination not listed here is not defined. Please note that these timings are estimates and not accurate. For instance, the Watchdog timer set to 1 second might not wake up exactly 60 times per minute. The reason is that the accuracy of the 128 kHz oscillator varies drastically depending on the input voltage VCC and the temperature. For instance, in the Arduino setting in the normal room, the oscillator will have a frequency of around 114 kHz and not the advertised 128 kHz. It might also vary from device to device. The main purpose of this oscillator is not accuracy, but a low power consumption. We briefly mentioned the WDT-ON fuse just a minute ago. It is a fuse that, if programmed, ignores the WDE and WDIE settings in the control register and makes sure that a reset is always performed. Please note that the default values of this control register is all bits equal to 0. That means the Watchdog timer Prescaler is set to 16 milliseconds. Hence, without reconfiguring the control register or kicking the Watchdog 16 milliseconds after the program started, a reset occurs, and it keeps resetting. Do note that old bootloaders for the Amiga waited for 2 seconds to receive a signal through UART to reprogram the flash with a new user program. These 2 seconds are a lot longer than the 16 milliseconds, and hence the Atmega could not even be programmed any longer, since it kept resetting in the middle of the bootloader waiting sequence. Like for the sleep function, the AVR library has helper functions for the Watchdog Timer as well. There is a WDT_enable call which enables the system reset after the specified time given as a parameter. To kick the watchdog, WDT_reset can be used. Do note that there is no function call that enables only the interrupt functionality of the Watchdog Timer. That the software developer has to do manually. That's all about the Watchdog Timer. The next periphery that we have to introduce is the Brown-Out Detector. That what you see right now is called a blackout. During a blackout, the nominal voltage of, let's say, 230 or 120 volt, or in our case 5 volt, drops to zero. This power cut might happen from time to time at home if there's a fault somewhere and power cannot be supplied any longer. Blackouts can also be used to reduce the load for power plants. The less severe version of a blackout is called a brownout. During a brownout, the voltage drops significantly, but not to zero. For instance, incandescent lamps don't glow that bright anymore and return back to the usual brightness after some time. Or in case of solar-powered devices, a shadow or cloud over the panels might cause a brownout. The Atmega is equipped with a detector which is able to reset the system in case the supplied voltage is insufficient for a flawless operation of the hardware. If the voltage drops below the threshold, here baud-, an internal reset is activated. It stays active till the threshold of baud+ is crossed again. After a timeout in which the voltage does not cross the baud+ again, the reset signal is removed and the Atmega restarts its application. The thresholds baud- and baud+ are based on a value called baud plus minus a hysteresis voltage divided by 2. According to the datasheet, this hysteresis voltage is constant at 50 millivolts as tabulated here. Then, the only question that remains is, what is the value of baud so that we can calculate the thresholds? It turns out that for the Atmega 328P, the setting is stored in the extended fuse. Again, the location depends on the Atmega that you have. For other Atmegas, the Brown-Out Detector trigger levels might be stored in other fuse bytes. Please consult your datasheet to be sure. For the Atmega 328P, there are 3 bits reserved to determine the trigger level, which can be disabled or set to 1.8, 2.7 or 4.3 volt, each of them with an inaccuracy of around plus minus 0.2 volt. As an example, if the fuses are set to 110, baud- would be 1.8 volt minus 25 millivolt, and baud+ would be 1.8 volt plus 25 millivolt. The 25 millivolt are half of the hysteresis voltage. The Brown-Out Detector might not be required when the system sleeps. To avoid wasting a significant amount of energy during the sleep phases, it can be deactivated by software as it is indicated in the last column of the table. To deactivate the baud, 2 bits are to be configured in the MCU control register. We have the baud sleep enable and baud sleep, and you might already guess, due to the presence of the enable bit, there is again a sequence to follow. And you're right. In a first step, both bits need to be set. then BODS is set to 1, while BODSE is cleared within 4 clock cycles to write a new value to deactivate the BOD. In addition, within the next 3 clock cycles, the sleep instruction must be executed. Otherwise, the BOD is reactivated again. Since the timings are somewhat tight and quite short, the AVR library recommends to set first the sleep enable bit, then disable the BOD, activate global interrupts, and issue the sleep instruction. After the Atmega is woken from sleep and it continues to execute its program, the sleep enable bit should be deactivated again. Okay, that is all about the Brown-Out Detector. I will give you some practical examples about how much the power consumption can be reduced. Also some hints and tips are given. Now, there are several reset sources, and it might be important to know what device reset the CPU. It could be that the battery is faulty and hence the Brown-Out Detector reset the system, or the program crashed and the Watchdog Timer kicked in. After the system recovers after the reset, it might be important to know where the reset came from. However, the system is reset, so everything is set to 0 and from the start. Fortunately, that is not the case. The MCU status register has 4 bits and they are set according to the last reset that was issued. In software, by checking which of the bits are set, a watchdog reset can be distinguished from a Brown-Out reset, external reset, or a power on reset. This register could also be very useful if unexpected resets occur in the system. Important to note is that this register should be read out as fast as possible, since the next reset will overwrite the value for the last reset that occurred. And in the end, some hints and tips which can be avoided easily if known. Usually, the sleep modes deactivate peripheral hardware. Usually. That means there are situations that this is not the case, which could result in an increased and unnecessary power consumption. For instance, for all sleep modes, the ADC should be deactivated manually and in addition in software. The same is valid for the analog comparator, which is automatically deactivated in the power down, power save, and standby sleep modes. However, while this is true for the AC and could also be for the ADC, there is periphery the analog comparator depends on. For instance, if the analog comparator is configured to use the internal reference voltage to compare against, while the analog comparator is off, the internal voltage generator is not, happily eating the battery life away. The same is true for the 128 kHz clock. If the Watchdog Timer is active, so is the internal 128 kHz clock generator independent of the main clock. And we saw in the tables earlier how costly in terms of current drawn this luxury is. Therefore, if the Watchdog Timer is not required, make sure the fuses are unprogrammed accordingly and the WDT is turned off, which in turn deactivates the 128 kHz oscillator. Let me show you a short demo of the exercise that you will find at the end of this chapter, covering everything that we had in this and the previous chapter. I will show the power consumption in various settings and with different voltages. It turns out that we can run the program of the exercise in the nanoampere scale while the Atmega sleeps, dramatically extending battery life. But maybe you are even better than the solution given in the exercise. Let me know.
I have here the Atmega 328B in this Arduino board and it's connected via USB, and as you can see I opened the USB cable and connected it to the 5 volt. so that I know how much current this entire board draws. I have my ampere meter here, and this is the voltmeter. So let's see what happens. Let me connect it. Initially it was at 45 milliamps, but now it came down to 35, 36, and occasionally it goes up to 37, 38. This occasionally happens every 4 seconds, and as you can see, this TX LED is then blinking. So this program wakes up and tries to transmit the heartbeat. The program that runs on the Atmega is the solution of the following exercise. And USB runs around about 5 volt, so we have here 4.98 or something like that, so close to 5. Now I'm going to extract the Atmega and put this into a breadboard. Same program, the only difference will be it will run at 8 MHz instead of 16 MHz. And the advantage of the breadboard is we don't have to power the entire board, but only the Atmega, and then we will see what the power consumption is by then. I extracted the Atmega. It is located here, running at 8 MHz. Brown-Out Detector is off, and I did all the wiring. Everything that's blue is ground, everything that's orange is VCC. So you see here, for instance, this is VCC, this is avr-gcc. Here's the capacitor connected to a ref, which removes a little bit the noise on avr-gcc in case there is some. Here's my pull-up for reset, and I connected this LED with a 330 ohm resistor, and it is connected to the TX pin. So if this Atmega sends some data through UART, this LED will blink. I did not connect any programmer to this LED, so we don't see that data comes out, we just see that data has been sent. And I have my voltage divider here, which takes the 5 volt input from this board and creates a lower voltage so that I can simulate the drain in batteries. And then this one is connected to ground, so only power comes from this board. I connected the ampere meter between the output of this voltage divider and VCC of the Atmega, and the voltmeter is measuring the output of this voltage divider. Basically it measures the voltage that is fed in via VCC into this Atmega. Okay, let's turn it on and let's see what happens. We see here around about 5 volts come out of this voltage divider, and after initial flickering here I do not see anything. So I'm not even sure if this Atmega actually runs. However, every 4 seconds, I'm not sure if it can be seen in the video, but every 4 seconds this LED blinks. So let me reduce the scale of the ampere meter. And we see that now it's around 6 microamps. However, every 4 seconds it goes to around about 20 to 40 microamps. Earlier, the Atmega running at 16 MHz required 30 milliamps, which we reduce now to 6 microamps. So let us see what happens if I reduce the voltage that is fed into it. Oh, 4.7 we are now. It's a little bit flimsy. So 4.5. So now it's at around 3.3 volt input, and we save another microamp. And still every 4 seconds this LED blinks. Let's reduce it further. And now we see that the ampermeter is not sensitive enough to measure this current anymore. We can further reduce it, but it doesn't make any sense. We don't see any power consumption anymore. So I increase the voltage again to around about 5 volt. The implementation is as such that if the voltage reduces, then also the frequency of this atmega reduces, but if the voltage increases again, it does not increase the frequency and it does not come out of the power down mode. And that is the advantage of using a Brown-Out detector. If the Brown-Out detector is active, which is not the case here, then the system will come back online once the voltage increases again. As you can see, we can save lots of power and increase the battery life if you do not use the Arduino board with all the functionality that it offers. The programmer, the power supply, and so on and so forth. As alternative, I have an atmega Mini Pro here, running at 5 volt and 16 megahertz. This is an atmega 328P. It has the same functionality as this one, just the packaging is different. And the Arduino Mini Pro does not have a programmer, so it does not need to power it. Power again comes from this Arduino board that I use as my ISP. So let's see what happens if it turned on. I put it again to milliamps. And we see that after an initial spike, it settles at around about 1.1 milliamps at 4.7 volt or 4.8 volt. If you look closely, you might see that this LED is glowing. Hold it closer to the camera. It glows because the internal pull-ups are active. If I switch to 3.3 volt, in this case this also works. Current is halved roundabout, so I can switch to microamps at around 3.4 volt. I still need 670 microamps. This is due to the fact that the LEDs are glowing here, so they consume quite a bit, and it is still running at 16 megahertz. So currently we run out of specifications. So if we could desolder it and put it onto the breadboard, this atmega will consume exactly the same amount of power that we saw earlier. And that concludes the practical session. I just wanted to show you what's the possibility and how much power you can save and how much you can extend the battery life. Head over to the exercise, try to reduce the power as much as possible. Maybe you can beat even 5 microamps and go into the nano amps range that you cannot measure anymore with these kind of ampermeters.
Let me shortly recap what we did in this chapter. We talked extensively about how the power consumption of the atmega can be reduced. The MCU is equipped with a power reduction resistor. However, just to be on the safe side, it is always advisable to manually deactivate the hardware before cutting the power. We also talked about many sleep modes that are supported and how to wake up from them. We discussed scenarios which helped us to decide if the CPU should be clocked fast to complete the computation in a short amount of time, or should it be slower, which then results in a shorter sleep time since the computation takes longer. We cannot always say. Ideally, If there are fixed time requirements caused by communication or ADC sampling, it is advisable to clock the CPU such that both time requirements are similar and in parallel to maximize the power-saving sleep period. We also introduced the general purpose I/O register. The Atmega has 3 of them, which all can be used by the software developers or whatever they see fit. The registers are not used by the compiler and do not exhibit any side effects, like for instance the DIDR-B or port B register. We talked about 2 new and interesting peripheral components. The Watchdog Timer, which is always available in all sleep modes and therefore predestined to wake up the Atmega in fixed time intervals. And the Brown-Out Detector, which can reset the MCU when the input voltage drops below a configured level. And what is next? In the next session I will demonstrate what some of the ways are to debug a user program on the Atmega. There are several options such as simulators, which are easy to use, but come with the disadvantage of being unable to simulate the physical environment embedded systems usually interact with. We will see alternatives such as the debug via interface and how to use it. While hardware debuggers cost money, this course does not require one, since there exists a free and open source solution which serves our purpose. But before that, have a look at the exercise. Reduce the power consumption as much as possible. Maybe you have even better ideas than me when you study the supplied solution. In any case, let me know how it went and what you achieved. I also always learn something new every day, and with that, I wish you lots of fun in the exercise, and then I'll see you again in the next chapter. Thanks for watching.